good afternoon. My name is Shachar, and thank you, Dr. Tadir, for the introduction. Thanks the Institute for allowing us to make our presentation. I think this technology is, I basically today will concentrate only on one aspect of the technology, which we title lensing of magnetic field or lobe magnetic field. In both cases, the combination of the electromagnetic sets of equations, which is basically Maxwell standard sets of equations in a dynamic time domain, and as it is modified and attenuated through a set of optical characteristics, which is basically Snell law and Fresnel. And you'll see how a simple observation while designing the system led to some efficiency that otherwise could not be understood. On the face of it, what we've seen is through our experimental data, we've been seeing some repeated regularity of the relationship between the magnetic field behavior, the field shape, or this geometry, and the field intensity, or what we call the flux density maximum axis. And so, let's go. So I'll just give some brief. So as I said, I will concentrate very briefly only on one aspect of the technology, and I think that's the aspect that lend itself to its viability as a commercial device, as opposed to theoretical. Let's build robot using remote navigation, because it's becoming practical because of the inverse law. And so few of the concentration areas of the company development in the robotic area or remote navigation, electrophysiology, which is our initial focus, and Dr. Gang will talk about the clinical relevance of this and why efficiency, efficacy, and safety are part and parcel of the use of technology. In the GI area, which we are now building our second generation machine to use for internal medicine and to do such items such as guiding a pill cam, an untethered device through the GI tract to take the pictorial representations of the esophagus, the stomach, and the small intestine and the colon. Interventional cardiology in the areas of valve placement, valve repair. In neurology, guiding catheter stereotactically through complex vasculatures or through predefined a map that can avoid some critical areas of the brain. And then, of course, the use of that for internal medicine, OBGYN, IFB, and so on and so forth. Next, please. I avoided all the statistics about the business because the idea was just to make some presentation associated with the technology and its ramification on the use in medicine. And so some of the important feature about the system is around 1400 Gauss in the center of the patient, which allows to, in around 1.6 Tesla meter of translational. The machine is capable of carrying 6 degrees of freedom, 3 translational degree of freedom, and 3 rotational degree of freedom without impediment. The machine works roughly at around 200 millisecond time domain, which Dr. Gang will demonstrate the timing, how that is correlated to clinical relevance. The footprint of the system is around 2 by 2 or so square meter, and the height is roughly human size. The weight of the system, because of the inverse law, is roughly around 20,000 pounds, so it's around 10 tons. And the power requirement is 50 kilowatts. Next, please. So just to demonstrate, a 3 grams of tool within the human body will require 20,000 pounds of equipment and roughly 50,000 watts of energy just to drive 3 grams of magnetic pallet within the human body because of the inverse law. And of course, the size as human, if you just take pole-to-pole size for inserting a patient, which is roughly required around 650 millimeter between pole to pole, because of people that the mandate by FDA mandates around 300-pound patient must be going to the MRI bore, and similarly for our equipment. Okay, next. Just a typical layout of operating room. We have an operating room at our facility with a authorized animal lab that we conduct most of our animal studies at our facilities. it's a non-survival. So we have facilities in Madrid, which is clinically functioning regularly, and we have one that was recently installed in Korea, in Yonsei University. Next. The important part, as I said, I will concentrate only on one element of the system. We call that thing low magnetic field. And the entire efficiency of the system, I just want to mention that as we originally brought this concept to the hands of the most notable specialists in General Electric MRI unit, all of them are specialists in magnetics, meaning with the highest acclaim. They basically said it's impossible and the power requirement will be around 400,000 watts. And we are basically at around, we operate at normal around 36,000 watts, so you can see that it's an order of magnitude below that. And the reason for that is not because they were erring or had an error in calculating them, because we just did it on the wall. As we came in, the specialists immediately just rushed to the wall and did some computational tools, the basic Maxwell, and got to the point where he said, look, you need a power station the size of this room, you need, and it's being impractical to develop a robot of that size because it's very inefficient, very expensive, and it won't be usable. We demonstrated, I then demonstrated that there are two principles in optics that were absolutely necessary, not at that meeting, but subsequently. Two principles that would basically improve the efficiency of the magnetic chamber and the generations of the field relative to the amounts of power. One of them was the lobe field, and one of them is total reflection. As you know, when you emit approximately around 25,000 Gauss in each one of the pole faces, there will be 25,000 Gauss of magnetic flux density, and here we're roughly around 1,400 Gauss. When you emit this amount of magnetic field, you will have a field that basically emanates in the inverse law and will basically emanate outside of this thing. The FCC mandate that you will not have more than 50 Gauss beyond 12 inches anywhere or any equipment, and must be reduced to half Gauss, which is the Earth magnetic field, approximately 36 inches away from any piece of equipment. And therefore, the idea was, how can we resolve it without shielding the entire room? One of the main issues was the efficiency of the system is the ability of the system to carry the magnetic field as a closed circuit and still have as open surface to prevent claustrophobic behaviors that you experience when you go to the MRI chamber. And that's what the first principle was, total reflection. Again, an optical principle altogether, where magnetic field just emanate back and forth against the wall and eventually absorb within the circuit. And the second principle was Snell law, where we actually can lens the field by actually creating a field density that is along certain axes that can be predefined. You can predefine its geometry. Next, please. The two rules that allow us to do so were the ability to create a field that its shape, its geometry is predefined. And here we demonstrated three cartoons of three possible configurations of the field. Here is basically a calculating machine where you have a symmetric field. All the pole faces are acting, or the electromagnet are acting uniformly and symmetrically, and you can see the center is kept perfectly at zero. If you eliminate one of them, you'll find out that you create the saddle and you can create this geometry. Using this calculator, you can basically build any configurations of any space on multidimensional. So the field was then we understood that we can take the field as a multidimensional, a Hilbert space. We can then represent it as a field that is being attenuated or varying based on the pole faces. So what the great observation that we found out were that, can you go back for one, please? That the field is can be modeled onto two elements. One, the density of the field, and second, the geometry of the field. Basically, what we created, the sets of dioptria that you have in the optical lensing were able to be combined. We were able to combine it with the principles of Maxwell. And to do so, we understood that there is one element that governs the performance of the field, which is permeability of the material, and the second one was the dielectric. So by using the two elements, we were able to produce a lens, a magneto-optical lens that direct the field based on the location of the catheter. So if you have a catheter, wherever it is located, the position, orientation of the catheter is known to us. We compute the field and radiate independently 8 different coils to produce the field that basically allow the movements of the catheter from the actual position to the desired position based on the physician movement. So the physician moved the joystick to wherever he desired, and by setting up the actual position, the field is then trailing and producing the movement of the catheter, basically producing rotation and translational forces to move the catheter to its desired location. We do that so elegantly that we offer, most of the time we spend roughly energies in around 20,000 watts, meaning substantially, of course, orders of magnitude below the general electrical equation. Next, please.
So is the energy continuously or in pulses?
No, so we have a DC field that are slew at around 5 to 6 hertz. And it's a DC field, not an AC field, of course, not like MRI. And the DC field is generated by 8 electromagnets on a spherical geometry, whereby we basically treat it like a linear, although it's not a linear flow. So it's a linear where we can have a derivative in any one of the anywhere on the chamber. And there is an effective field that is actually absolutely homogeneous and uniform, which is 6 by 6 by 6, which travel like a flashlight, travels where the catheter is. Where the catheter center is, there'll be a ball around it that move with it in unison. And you'll see that this part of the technology enables some of the other efficiencies, so we can move with a dynamic object as the heart, we can move in unison with the beating heart, because we can move the center. This is not a fixed center where the magnetic field is in the center, but it moves dynamically with the catheter tip. So the catheter tip become the center of the spherical homogeneous field that moves continuously with the catheter. We'll show Dr. Gang will show you later the video of that. The critical things is, and that's what a student, the only thing you have to look for is not what is written and what are the standards, just for some anomalies or variation from the standards, and take it very seriously. We looked at the magnetic field and saw this funny behavior that every time we allow another material around the pole faces, we were able to actually shift the magnetic field to and basically shorten the distance between the flux line and create a flux line that are much more compressed. And this particular compression or lensing are the principle by which this operates. Otherwise, this machine will not be efficient and will basically obey the General Electric scientist approach, and you will need a massive power supplies, and it will be inefficient and unacceptable. Our machine is very elegant and capable of doing all that because of the lensing principle. The basic rule is that tangential components of any electromagnetic wave are discontinuous regardless of the value of the energy density at the interface. This continuity is related to the permeability of the two medium. So what basically this is for, if you just took a pencil and put it in your water, you'll see out there is a break. Of course, you'll see the optical shift. The optical shift is basically the relationship of the speed of light over the or the electric of the water. That's all there is to it. And so you can see the shift, the optical shift. These are not just an illusion. These are actually reduction of the speeds of light relative to the electric material. We did the same things in our electromagnetic. We basically created two permeability rules. We created a calculator that allows us to take a very, very low permeability, like 10 on the ring, and the pole faces of the magnetic field, the generators of the field is permeability, the mu is 1000. This ratio produce the angle is proportional to the shift. So you see that shift is been then emulated in electromagnetism. So we did it, and we were able, of course, to create fields that are highly dense. The flux density is very, very high based on our demand. Otherwise, you eliminate massive amount of energy to try to do the same job. Next, please. So basically, Snell law. And then, as you can see, the only rules that govern us is the permeability and permittivity of space. The index of refraction are the only rules by which we define it. This is the principle by which this particular robot is operating efficiently. Otherwise, it will be another massive piece of equipment that will be inefficient, very expensive, and of course, nobody will be using it. Next, please. An important item about because the principle of operation is that we are using catheters with a magnetic pallet that are inserted in the inside here. This represents around 7 French, around 2.45 millimeter in diameter. There is around 19 millimeters of rigid section. This is made, we are packing nanocrystalline magnetic particles inside that particular device, so we can pack high coercivity, around 1.45 Tesla, around roughly 1.5 Tesla of coercive force into this little 2 grams of magnetic material there. And that's allow the maneuverability. Dr. Gang will talk about it relative to its clinical use. Next, please. The Mozart? No, that's for Dr. Gang. He's going to be demonstrating that. No, dude. Okay, so it's working? Because I didn't have it on my system. So you can see the agility of moving a magnetic field. Remember, we're talking about massive amount of energy, and they're switching at around 200 milliseconds. And the reason for that is all our coils have a very, very low inductance. We fed the audio amplifiers, we feed the magnitude and directions of the field with basically the score, and the scores are the voltage and phase has been then represented here. So there is no animation here. This is real, just feeding an audio signal into the audio amplifier, class D amplifiers, and that's the results. And you can see the field strengths in relative to from the red to the green and blue, which represent the vector directions and the magnitude. Yeah, that's good. Yeah. Again, Maxwell in itself would have yielded results that are unacceptable. The ingenuity of the solution is one of our scientists named Laszlo Farkas was able to create a situation basically where we are not, yeah.
You showed angular function. It's wondering, you want to translate, for example, you would say the blood vessel.
Correct, we translate.
Full band, that's I assume is possible within the limits of whatever the magnetic field is. Is that possible?
Yeah, so there is 2 forces here. As I said, there is translational forces, which is the gradient, field gradient, and then there's rotational forces, which are just field. So field, everybody knows, you take a little magnet and you do like that, and you can move anything around it. Pretty much a simple thing. We don't need any explanation. Translational forces are much more complicated because they are associated with the fact that you need to have a very high gradient in order to translate. And you have to overcome gravitation and the mass. So you have to apply the second law of Newton in order to do so. So one of the ingenious solutions that came from one of our engineers was, hey, we cannot really produce this massive amount of gradient. So let's do something else. As you know, Gauss already told us that we cannot have a minima in magnetic field. There is a divergence theorem to definitely show there is no possibility of making a minimum force. So what he came up with, he said, what if our regulator produced this 8 electromagnet that dynamically always shifting the field, will produce a value where this is the minima, this is 0, and this is the gradient, the maximum gradient on each side. So the catheter is like cradles into that field and moves this way. This is how we do translation. The important part about our system, we call it dog on the leash. We basically have a very, very floppy catheter that we put a little bit slack in, and Dr. Gang will talk how he uses it in operation. And then we pull the magnetic field, pull the heads of the catheter, and then the rest of it just follow through. And so we give a little bit slack coming out to a device that's called an advancing device that will show you. Next, please. So just to summarize, as I said, we're only considering one principle, and the principles of lensing or loading the field. And you can see this is a normal flux line. The flux line inside the lens. These are 2 cores on the electromagnet. These are one electromagnet, another electromagnet. You can see that the lines are almost straight, and we can actually reduce their spacing as opposed to the inverse law requirement. We do that because there is a ring behind it that has a very low permeability versus this one. And the differential between them produce pressures on the photon, if I can call it a pressure, on the photon. So the photon are basically, the masses then are getting closer, so the flux lines are much closer, and then allow us to have like a flashlight. We can direct the electromagnetic field as opposed to let it expand. So these are the lamps. These are the type of coils we have, and we have basically applied this principle across the board. And that's the first machine and our second machine that we are building right now for GI. Next, please. I think that's the one who discussed that, snaking. Again, a joystick operated from the control room, remotely enabled to do that's the top architecture of our system. The system carries basically all the elements of the operating room, from echocardiography to x-rays to the motion of the bed, and all the other tools that the physician uses in his operation. Next. Next, please. Dr. Gang will deal with that. We have all kinds of safety devices. We build two levels of safety. One of them is, of course, the software writings and all the control levels that we insert in the software. But we have a heuristic manager, which is basically programmer logic control. We take all the parametric. For example, a catheter will not move in the heart more than 20 millimeter per 3 seconds. There's no point. There's no use for the physician to rush in the catheter. Therefore, if there is a position where the physician actually ran the catheter to increase the maximum forces on the system will reduce the amount of forces required, because the system knows that there is a heuristic manager says you cannot translate more than 20 millimeter per 3 seconds, no matter what. So no matter what the command, it's overruled the command. So we build a whole set of these safety devices into these Siemens-like module called PLC. And it's a wonderful tool because it's easily programmable, and it's a small little computer node that takes a lot of intelligence and can do a lot of stuff that you want to protect or control. So instead of just writing software, that's basically more for regulatory purposes, so the FDA will not cite us for not being safe enough. Next, please.
What are the range forces that you're generating?
We're generating around 16 to 25 and up to 35 grams, depending on the angularity of force in any one of the operation, in mode of operation. And in the GI, we're going to produce around 85 grams of force in order for us to cause the pylorus and then prevent from being stuck in the small intestine. Next, please. Our competitors. There is one competitor in the field named Stereotaxis. They are basically using a large permanent magnet, around 6,000 pound permanent magnet with motorized section, with a multiple 3-section large magnet that are basically moving motorized. So let's say you want to go from here with a 45 degree on the same plane. Then one set of permanent magnet will move relative to that angles, and they compute the angles required and get the gradients and do the movement. It's very slow, very basically 1980s technology, and could have been thought by Plato. Plato written very extensively on the issues of magnesia and Herculia. He wrote exactly that story. So we really didn't need to have the technology. It's our competitor, but we are actually gaining ground. This is our equipment in our operating room in the early stage. It's substantially improved since then. Next, please. Comparison. I don't think that this is a place we don't need to tout. No, go back, please. One. So just to summarize, we have an array of 8 electromagnets. We focus the field, its real-time control, its variable power availability, and no magnetic shielding is required. This is really an essential element. You don't need to shield the room, because hundreds of thousands of dollars to shield for magnetic. You have a variable geometry, a variable power, depending on your need. You have real-time control, near real time, so around 200 milliseconds. You are focusing the field, which is making all the efficiency of focusing the field, so you don't need to have massive amount of power. And then finally, this entire magic is because you have an 8 electromagnet. As you remember, we have 6 degrees of freedom, and then we have the entire manifold rotation. So to solve the 6 equation, we need 7 iterations. And to solve the issue of the entire manifold rotation, because the patients move, and we have to also rotate the field in its entirety, preserving the entire manifold of the X, Y, Z and the orientation, but rotate in the field relative to the patient, we need another degree of freedom. That's why we need 8 electromagnet. This solve, if you add another 1,000 electromagnet, it won't make any difference, because at 8 electromagnet we've covered the entire gamut if the system is spherical. And we build a spherical system, so the entire thing says there is a derivative in everywhere in this entire chamber. Guidance, it's a closed servo loop, so the physician can set basically a lesion characteristic or interest to him. Yeah?
So does the Catheter respond to the control? So is there any delay between you giving a command?
Yes, 200 milliseconds. 200 milliseconds. And basically it relates to the amount of energy that are sitting in the coils that has to be moved back in the back EMF to the capacitor bank. So we have a very large, we have a capacitor bank this big, which is around 30 picofarad, with a superconductor nanoparticles capacitors, which is fantastic. Otherwise, we'll have to have something the size of this wall and to store this energy. And we're putting, and the other element that can define the time domain is, of course, the latencies associated with your inductance. So we have very, very low inductance on the coils, very large wires, and self-cooling. 3D space, 6 degrees of freedom, linear and lateral path, 3-axis, the control, full automatic mode, contact sensor, I mean, varieties of features. Dr. Gang will talk about them because they are really inherently part of the clinical needs of the system. Next, please. Some of the teams, Laszlo Farkas, please. Laszlo, David, Bruce, Sean, David, and Steve. And of course, let's see the leading group of the technical team. Next, please. We have, of course, a new generation machine, much smaller, around 2,700 pounds, as opposed to 18,000 pounds, roughly. And it's for internal medicine. It's for tethered and untethered device. And the reason for its size reduction is because the probe faces are much closer, and the geometry is not spherical, but cylindrical. So we have a cylindrical set of coordinates. It's a whole different math in a whole different way. There are no derivations that are linear because of the cylindrical structure. But since we are dealing with almost a linear movement in the internal medicine, we do not have a very complex multi-rotational geometry and no moving parts to speak of. It's much easier to solve it with that type of approach. Here we have basically solved another big problem. In that area we had used we are basically using an untethered device. We have an additional degree of freedom, 6 degrees of freedom, because you basically have to levitate the pill cam, the camera. And to levitate the pill cam, we're using another field called the lens law, where we basically object or fight the gravitational field and eliminate the mass. As you know, mass and accelerations and in the general relativities are one and the same. And so we eliminate the gravitational field, then the mass is being reduced, and we take an 8-gram device and reduce it to roughly, with lens law, roughly to 1 gram in mass relative to the amount of force, the lens law. And then by that we have to have a very small amount of energy to create the vector setting and the translational forces. Why? Because the mass has been reduced. So FMA, we just play the game, and it's all very simple. This is again a very ingenious solutions of one of our very talented engineer, and that's the new machine which will be available for in the future for colonoscopy, internal medicine, IFB, OBGYN, biopsy, and variety of other issues. Next, please.
So with that,
yeah, just show you if it works. I should show you a prototype of the concept. In a minute, you'll see the GI tracts movements of the pill cam. So that's how it is. The translational forces are generated by because, as I said, these are cylindrical, so there is holes. If it's spherical, you can find a derivative anywhere else. As you understand, there are in partial differential equations, there are areas where you have holes. We've been able to find solution to that, and there was one, and when you have the cylindrical geometry, you have holes that cannot be covered because we have a set of 2 electromagnet sets that are separating, creating the cylinder. And so to solve it, we basically added another translational forces. We compensated for the geometry holes by moving the bed in and out and solve the problem. Next, please. Yeah.
will that be to move an untethered pill? Or
Untethered pill. In a tethered pill, you basically, in the customary place, you do forces, and then you can always have a driver like we have in the cardiology side, that basically push the extra slack for the catheter. Okay, so basically the design. Replace next.
What forces do you have to overcome? The peristaltic forces?
It's around, the peristaltic forces are between, first of all, it's random, so we have to worry about it, because it's basically randomly moving, and you cannot really predict. There are not some regularity to peristaltic. And so the regulator should be fast enough to catch up that there is forces that are either rotating or translating the device, and be able to respond to it by actually putting a brake on the system or accelerating to meet the requirement. So we build all this regulator smart into the thing. As I said, it's 45 grams and up to 85 grams of force, while in cardiology we only use 16 to 25 roughly. We never use more than that.
So this will be for both upper, middle, and lower GI?
So this will be, so from the sternum, 1 to 3, from the sternum we can go just, this cavity or the abdominal cavity will be available to us. And of course reproductive organs. From this point on, it's the second machine which we have in CGCI. And the third generation, which is what we're doing next year, is to build a neurology piece of equipment. By the way, our estimate is to be around 600 pounds. So 600 pounds, 3,000 pounds, and 18,000 pounds. That's the inverse law. That's it.
And how many degrees of freedom on motion with the pill?
With the pill, it's 6 degrees of freedom. Otherwise we won't survive, because basically it's always in an accelerating mode. Remember, we have permanent magnets inside the device that have very high coercivity, but permanent magnet, and they're always in an accelerating mode. And so we need to be always to put a brake. So we have an AC and DC fields here. Here the DC field is around 6 hertz, but the AC field is around 5 kilo. So we have 5 kilohertz for creating the lens, so it's always buoyant and always in a semi-levitating state. And then the DC is basically the gradient that allows the translational. So we have buoyancy, translational, and rotational forces with the DC. So DC-AC combination.
So you can translate the full 3 spatial dimensional axes?
Completely. 6 degrees of freedom and in 3D space without any impediment or invariant to any geometry.
How do the fields impact the detectors? I assume you have some optical.
So the camera is operating. It's a combination of CCD and other technology, but they're operating at a 14.36, which is the standard video module that can penetrate around 8 inches of body with the energy necessary to penetrate the GI tracts to the video, because they have a monitor that kept it are attached to, like a Holter monitor that receive the video data. It's a 32 frame a minute.
Is this one only for diagnostic or?
So phase 1 is diagnostic for the pill cam, and the second phase is for therapeutic, where we have a biopsy tool, and the other side, the camera is in the first dome, and the other side is empty. We will use that to nest sets of tools for biopsy, medication delivery, and varieties of other tools.
It's not done for surgery per se?
No, right now it's for diagnostic purposes, and that's what we want to know that you have that you don't have any polyps in the con, basically. Yeah.
So what's the positioning and resolution? So
Okay, so it's a 1 millimeter required. In order for us to get a good control over these things, we need 1 millimeter. What attenuate or mitigate the need for an absolute accurate 1 millimeter is that the magnetic field is always very, very uniform along that, like a tennis balls around that particular pill cam. It's much smaller, but it's uniform. It moves with the catheters. We know the position. If there is an error 1.5 millimeter, it won't make a difference, because it's nested in a continuous ball of uniform magnetic field. Any questions? Thank you very much. Appreciate it.
Sure. There's a take-home test at the end of this. So can I have a show of hands? Who here does clinical medicine? Anyone? Medical students? Anybody do clinical work? Or is everyone here a one? Two, of course. Yes, of course. And the orthopedist, of course. Right. All right. So in that case, I'm only going to show the picture, my family pictures. I'm not. All right. So I'm Eli Gang. I'm a clinician. The joy of working with Josh and with the team is that. So you want to go straight to the down here? You want to go like so? Thank you. This is my only slide. No, there are more. This is the team, and the joy of working with this team, as you can imagine, is well, this is on a timer, so it's not on a timer, is it? It may be very sensitive. Okay, is that I can come up with questions, dumb clinical questions, and turn it over to the very smart engineers, and they come up with brilliant solutions. And that is really the joy of integrating clinical medicine with engineering. And you can make a wish list of what you would like things to do in your clinical practice. And sometimes the engineers can overcome all the technical hurdles and come up with magnificent machines such as you've seen and such as we're planning for other aspects of clinical medicine. So this is the team. Let me address some of the questions. What are the clinical needs addressed by technology such as robotic in cardiology? And specifically, I'm an electrophysiologist, which is a glorified title for a cardiologist that does medicine that deals specifically with rhythm disturbances of the heart. And you've got chaps like that at UC Irvine. I know them, and they do similar stuff, but they do it manually right now, as I do it every day, but we're hoping to translate it into the robotic arena in the future. It's already going on in Europe and will shortly be going on in the United States as well. We need to move a catheter, 6, 7, 8 French catheters with electrodes at the tip, which can both record bipolar and unipolar electrograms, electrical activity in the heart, and also for therapeutic purposes to be able to deliver energy, ablative energy through the tip. Most commonly we use radiofrequency energy. Cryo-energy is also being developed, and laser energy is also being delivered, but by and large, overwhelmingly, we deliver RF energy to generate enough thermal injury to be able to ablate, to be able to change the cells, to eliminate their electrical function or to modify their electrical function so rhythm disturbances of the heart can be literally cured, or in any case, significantly modified. So what robotics of the kind that Magnetecs builds allows for great precision of movement of mapping and ablation catheters. It allows reliability of positioning of the catheters and ability to return to exact anatomic targets. Right now what I do in my day-to-day practice at Cedars-Sinai is manually move a catheter, and it takes a lot of experience and a lot of training. Our program now for the fellows is a 2-year training program in clinical electrophysiology after they've already done general cardiology, because you've got to think in 3 dimensions, look in 3 dimensions, move catheters in a non-static environment of a beating heart and try and get back to the same place, which can be challenging and difficult, sometimes impossible, and a lot of that is overcome by a robotic system that remembers the coordinates where you were. You can always go back within the resolution of the map that we use, back to the same exact spot again and again and again to sample electrical activity, to sample the effects of what you did, and to make sure that you've achieved the purposes that you want. So I'm going backwards. Better procedure outcomes. We hope for higher success rates, particularly in the 800-pound gorilla, which is the rhythm called atrial fibrillation, which is by far and away the most prevalent, especially as the population here and in Western Europe ages, the most prevalent rhythm disturbance that we have to deal with. About 60 or 70% of the ablations I do now are for atrial fibrillation. Decreased mechanical complication rate, most notably perforation of the tissue of the heart. Imagine you're pushing a relatively stiff catheter right now and delivering heat energy at the tip of it. There is a 2 to 3% incidence of actually poking a hole in the heart when we do this. We explain that to the patients. We know how to deal with it. We know how to recognize it. But it's still scary and potentially fatal. Using the floppy catheters that I'll show you, which are the last distance of it, last 20 centimeters or so, are totally floppy. You have relatively much softer pressure against the wall And as Josh was saying, you've got the dog on a leash concept where the magnetic forces move the electrodes, but we're not pushing from behind. And so it's theoretically and practically a safer environment to work in. And finally, reduction in procedure time. This great accuracy of the system we've yet to prove this, but we think it'll reduce procedure time and reduction in radiation exposure to patients and to staff. God knows how many hours of radiation I've been exposed to in the 20 years I've been doing this, because a lot of this is done under fluoroscopy. We hope that a lot of that will be eliminated by being able to use the robot and sit outside and with a cappuccino or an espresso in hand, move the joystick and get the catheter to go where it needs to go. And from a hospital standpoint and from an economic standpoint, increasing the throughput in the EP lab is important. There's a huge backlog of patients that cannot be treated because these procedures typically take 3 to 4 hours at least per day. I'm exhausted at the end of a day like that. If you can do 2, you're lucky. Usually you can only get 1 done reliably. We project, and we'll have clinical data in the next year, that the throughput in the lab and the efficiency will be significantly increased. I'm going to skip through this. These are the early prototypes that we built, and Josh talked about the magnetic field, so I'm going to just skip this. This is looking down. You can see 4 out of the 8 magnets. You can see the magnetic fields are pointing in one direction, and the tip on this catheter is aligned with the magnetic fields, but you can change the magnetic fields by changing the polarity and the intensity of the magnetic field in each of these 8, done as far as the human eye is concerned. It's instantaneously, 200 millisecond delay, and you can realign the catheter tip in 3-dimensional space, and that's what we call our torque fields. And you can do push-pull by having field gradients so that you can actually go towards the differences in magnetic field illustrated here, so that the catheter can actually move in the direction of the stronger field. This you saw, the CGCI Symphony. There was a question about, I'm moving quickly because it's already 1 o'clock and we're way over, but there was a question about force generated at the tip of the catheter. We measured it in vitro, not yet in vivo, and depending on how much catheter is extruded from the tip of the sheath and also which angle you're at, you can get up to 25 or 27 grams, and actually with the change in pole face that we've instituted in the clinical machine, you can probably go over 30 grams, and that's about where we want to be. We want to be between 15 to 30 grams. That's been tested in vitro in preparations of thigh muscles where lesions have been created with RF energy, and we've seen what is too much energy and what's too little energy and what causes a steam pop. So we want to be between 15 to 25 grams. You get effective transmural lesions even at 10 grams, depending on how you line up the catheter. So this was a paper that was just published in Circulation by our group, a couple of weeks ago, summarizing the animal work that we did at Cedars-Sinai in the Davis building. This was our animal machine, which is on the same lensed principle that Josh described to you. The clinical machine is larger. This was good enough for a full-sized pig. These were in vivo studies of navigating the catheter inside the pig, mostly in the left atrium where most of the atrial fibrillations come. So for the couple of clinicians who were here, we actually come in from the right side, the venous side, poke a hole in the septum, which is what we do every day. It may sound barbaric, but we do it every day with a needle, under guidance, of course, get the catheter into the left atrium, do our navigation, move the catheter around with a joystick in our case, manually in the clinical case every day, create a 3-dimensional image of or a shell of the chamber that you're in. It could be any of the heart's 4 chambers. Most of this work was done in the left atrium of the heart. And then just to show where we were, we actually delivered RF energy and we tagged it. We actually weren't planning to ablate in this particular set of experiments, but we still got beautiful transmural lesions nonetheless. Okay. The catheter, I have another picture of it, but the issue of the catheter is that this last 20 centimeters of it is actually very floppy, and this is the tip that Josh showed you, standard quadrupolar 4 ring electrodes that are connected by wires back to the amplifiers and to the source of energy for delivering the ablative each place where we've frozen each place where the catheter was. So this is the left atrium of the pig, which is different than the human one in the sense that the appendage is massive here. It occupies half of the volume of the left atrium. So this is the left atrial appendage of the pig. These are the two major pulmonary veins. The humans have 4 pulmonary veins. And essentially, we got the catheter everywhere within the volume of the pig's left atrium. We were able to reproducibly, in the 10 pigs that are reported, get to all the sites, especially after a small learning curve. We were able to reproducibly get back to each site in an automated mode. I'm skipping around a little bit, but forgive me because I don't have that much time. When we would tell the catheter, we've been here, and tag it, pull the catheter back a few centimeters, 1 centimeter, tell it, go back to that spot. You're on your own. Get back there. You know where the coordinates are. The 3D coordinates, go there. And invariably, it always gets right back to the spot on that 3D map. This is on our 3D map. We had a circular set of lesions just to show where we were. In fact, at necropsy, you can see a transmurality. These are lesions, necrotic lesions from application of RF energy, which had the same size and the same geometry of the lesion set as we showed it on our map. This is highly correlative. This is actually histology, H&E slides. The transmurality overall was about 79%. The red H&E is the necrotic tissue. Bruce, with your technology, you don't even have to do staining or preservation of tissue anymore, but you've eliminated. Pathologists are now all on pension. Yeah, right. More recent studies, again in the beating pig heart, we create a 3D geometry. The geometric tool in this particular case is made by St. Jude Medical, by the way. So this is the so-called Navix map. These are 2 views of it. You can see the homunculus here, 2 different views of the left atrium. Each one of these dots represents RF energy. We were able to move with great precision the catheter tip so that it actually encircled the pulmonary vein, and I'll tell you in a minute why that's important, and got contiguous overlapping lesions, and tagged each one of them on the map. And in point of fact, at necropsy, this is actually a hematoxylin blue stain. These are transmural lesions. The blue, these are necrotic tissue. The pink ones are more viable tissue. And we got transmural lesions delivering RF energy at conventional tissue energies. And this is an H&E slide, and these are also, this is also showing essentially transmural lesion. Little mural thrombus here. We may not have given quite enough heparin. This is an epicardial ganglion, which has shown thermal injury. Actually, that's important to us. We think that eliminating epicardial ganglia in some arrhythmias is important, and we're going to be doing some research on detecting the signals from these, which hitherto have not been detectable in vivo in humans, but we think, new technology for detecting these signals. This is our lab, as it is the clinical lab in Madrid at La Paz Hospital, where we've done our first 40 patients. And we recently celebrated last week the fact that we got CE mark based on the data that we obtained there. This was just a mapping study. You asked before, have we done therapy in the GI tract? No, and we haven't done therapy yet in humans. Our next trial, which will start in the next few weeks, will be actually delivering ablative energy. But the first 40 patients in Madrid was just showing that we can reliably and safely go to where we said we can go in each of the 4 chambers of the heart. And then we pulled out the patient out of the magnetic field, and then the patient got the standard therapy that they would have otherwise gotten with manual manipulation of the catheter by the electrophysiologist, Dr. Jose Marino, in Spain. I'll show you some of the clinical results. Basically, they were excellent. We had great reproducibility. Here's a close-up view of the catheter that's used. This is the distal pole here is also platinum metal. It is impregnated by magnets, as Josh told you, neodymium magnet particles that give us the coercivity that Josh described. And this is still the floppy section. And these interelectrode distances are clinically normal, what we use every day, so that we're not rediscovering the wheel as far as how we record or how we ablate, only how we deliver, guide the catheter. This is a close-up of it. This is just one iteration. There are other iterations of where we will place the magnet depending on how we build it, who we build it, what our needs will be. This is what the workstation looks like in Madrid. With this particular image, you don't actually see our large monitors here, but this three-dimensional joystick here gives us it's really a cool joystick, because as you move it in 3D, you're actually moving within the space of the heart, within the chamber, and it responds with great precision. We have a negative feedback algorithm, which we're not quite using yet, but it's part of our intellectual property, that where eventually, if you're up against the wall, you will have increasing resistance against the joystick up to the point that you will not be able to move it, so that you can minimize the amount of potential damage you can do. We have another joystick here in the current way we have the system built, which allows us to also rotate the image, also allows us to give slack or pull back slack. So we're basically working with two hands sitting here at the joystick. There's an RF generator over here. There's a screen here for the multiple electrograms that are generated by the catheter in the heart. So there's magnetic steering, slack control. Quickly, to tell you about the physiology and atrial fibrillation, there are 4 ongoing hypotheses, and there may be a combination of these in real life. The one that we think for paroxysmal atrial fibrillation is the most relevant is the multiple focus hypothesis, which is to say there are areas that are firing ectopic beats that shouldn't be coming there, should be coming from your own sinus node, your own natural pacemaker on the right side of the heart. In point of fact, a lot of people with atrial fibrillation have impulses coming from the wrong side of the heart, the left atrium, and frequently each of these circles represents a cartoon of the pulmonary vein, frequently from within the pulmonary vein. Sometimes we run into a single focus. There is a lot of research now on the mother rotor hypothesis, which means that electrical activity is anchored against an anatomic site, which anchors it, and there's continuous rotation around it very rapidly, which then sends out electrical signals in a centrifugal direction. Multiple wavelet hypothesis is less popular now. The French gave us a great contribution, other than wine, women, and perfume, about in 1998, a fantastic contribution by the group of Heidegger in Bordeaux was to show us that a lot of these premature beats came from the pulmonary veins in the left side of the heart in this cartoon here, and that in fact once they fired and found the atrium susceptible to these, they generated atrial fibrillation. If you were able to go into the vein and eliminate these, you were able to eliminate paroxysms of atrial fibrillation. So the whole science of ablating atrial fibrillation has been to contain these impulses within the left atrium by creating circles of RF lesions around this. We don't go into the vein anymore. It turned out that if you went into the vein and ablated them directly, you caused damage to the vein, which is very thin tissue, and eventually it got stenotic, which was, I touch wood, never had a case like that, but there were 3 to 4% sequelae of ablation, which is narrowing of the pulmonary vein. So we now ablate outside the pulmonary vein at the junction of the pulmonary vein and the left atrium, and try and contain behind this picket fence of RF lesions these impulses so they never emerge into the heart. In fact, histologically, you see a cross-section of the left atrium here and the left superior pulmonary vein here, and you see these little muscle bands or muscle fibers which embryologically extend. You would think the left atrium ends here, but it doesn't. These muscle bands actually go out into the pulmonary veins, and among these muscle bands are sites of firing, which we need to contain by creating lesions here, and as I say, kind of creating a picket fence around this pulmonary vein structure.
So the pulmonary veins actually have some smooth muscle cells?
Exactly, yeah. There's an embryologic growth of how the heart evolves. Right. What kind of lesion sets do you create? Again, Heidegger from Bordeaux and his group, Pierre Jailly and others have done a lot of clinical work, as have many in this country. And this is for persistent chronic AFib, but it also applies, of course, to all forms of atrial fibrillation. Do you just create a circle around all 4 veins, the 2 on the right, the 2 on the left? Do you create what's called box lesion, a set of lines, contiguous lesions across the roof and the floor? Do you do just the roof and then connect this to the mitral valve, do another line? And there are data suggesting the advantage of each particular set. But again, think of it. You need to move the catheter in a beating heart to create a set of contiguous lesions. Each of these circles is composed of points. Each of those points is a single RF application of 20 to 30 seconds, and it's got to be stable, and it's got to be on the spot, and some spots are ridges and mountains and valleys, and the catheter wants to fall off. Some of the beauty of our controller is that it forces the catheter to stay where it wants, and if the catheter wants to fall off the ridge, the controller pulls it back up to the ridge because it knows which set of coordinates it needs to stay on. So this is some of the beauty of robotics, to be able to create accurate and contiguous points that will make up this lesion set. This is from a real patient, one of the earliest ones I did, a three-dimensional construction of the left atrium. And each of these contiguous spots, this was done manually, by the way, created a circle around the left superior, left inferior pulmonary vein, right superior, right inferior pulmonary vein. This took hours. And I think that we will get even better accuracy and much more efficiency doing it with the robotic system we showed you. Here's a three-dimensional view of the left atrium. Each of these represents energy application. In this particular case, when we completed the circle, this is atrial fibrillation. Clinically, the ECG, the intracardiac electrograms, you see it abruptly stops. And the rhythm stops, and the patient is now in normal rhythm. Here's our system. Here's Jose Marino, the chief of EP in Madrid, sitting there. He's got the three-dimensional joystick in his right hand, the other joystick, the slack, and the view controller in his left hand. He's got lots of other things he can look at. He can look on the screen. He could look at an ECG. He could look at whole sets of ECGs. He could look at a chest X-ray. A chest fluoroscopic X-ray. He can look at an intracardiac echocardiogram. He can also change what he wants to display. We have a very large screen that allows you to, at the bedside and here, to bring what you want to the screen, take what you want off the screen, change the size so that you can really make the screen fit your needs. We have all kinds of this shows up on our control. We've enlarged it here. There's all kinds of information here, which I'm not going to go into each one of them, including distance from the target if you've gone automatically. Here we have a contact sensors. It's a specialized impedance sensor that tells us how close we are to the surface of the wall that we're trying to touch. All kinds of information is available here. Let me just show you, although the timing may not be, let's see, how do I get this to move? Yeah, okay. So this is not completely real time because there's the video aspect of it here, but it's close to real time. I think Jose tagged a spot in the we're on the right side of the heart. This is a patient, one of our patients in Madrid. He tagged a spot up there, and the catheter is slow. Is making its way towards the target on the 3D space that it was told to go to this spot. And you can see here's the distance to the spot. It's going to reach it and be about 1 millimeter, which is terrific, really. We're about 1 millimeter, give or take, on the beating heart from the actual target. And then he manually takes over and takes it back to the body of the right atrium and creates a map. We have two different views, right anterior oblique view, left anterior oblique view. He's moving it around. He's sampling various parts of the right atrium. So this is, I'll move on. Here he is in the right atrium. Here we are in the coronary sinus. Those of you who remember some of the anatomy know that this is a vein coming off the floor of the right atrium and hugging the back of the left atrium, a critical structure for us in electrophysiology. Also in placing special kind of pacemakers and defibrillator leads. If we can look through blood with OCT, for example, we'll know where the branches of these things are. But we can no, let's go back. So if I put this here and click on it, I should be able to make it move. Here we go. This is not easy. This is not easy with your hands, let alone with the robotic system, but there it is. The catheter is in the coronary sinus. It's mapping the coronary sinus. It's already created a map. That's how we have the image. He's moving out to the right atrium, to the superior vena cava, and he'll readily go right back into the coronary sinus, which is a site of rhythm propagation, rhythm origination sometimes. We've ablated an accessory pathway here in a patient. And there's all kinds of important information in the coronary sinus that this robot allows us to enter repeatedly and reproducibly. Here's a phenomenal illustration of what the system can do. The catheter has gone, you don't see it here, but the catheter has gone across the transeptal area, looking from the left side of the heart, from the left shoulder. It went down across the mitral valve, which isn't shown, into the left ventricle, across the aortic valve. It's now in the aorta, the large artery that that leaves the heart. We are now going into one of the coronary arteries. I'm not saying that we'll clinically ever need to do it, but I'm just showing off the incredible versatility of the system. With a joystick, Jose is manually moving. That was the right coronary artery. He's going to go into the left coronary artery. There is nothing out there right now that's comparable to this, that can create this kind of flexibility and real-time motion of a catheter inside. He's back in the left ventricle.
So is that the left anterior?
He didn't go that far. He went into the base of the left coronary artery, into the left main. We didn't want to mess around too much. We don't belong there. Angiographers go there, but we weren't taking pictures. We were just sampling anatomy, really.
Can you define the trajectory?
Yes. Yeah, once you have a map, you can define any trajectory. You can tell it, I want you to go here, 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 and it'll go to every point. You can create a circle and tell it, that was what I was trying to show earlier in the animal model, create a circle and tell it to go clockwise, counterclockwise, any degree on that circle that you want to go to. I won't...
You have to have a full angiographic map.
Either an angiographic map, which you digitize, or you make all the movements first and create all of these spots, and then the machine will integrate where you've been into a 3D shell, and then you move within the coordinates of the shell. This is a clinical study that we did. That was the 40 patients I spoke about, registered in Washington on the clinicaltrials.gov, and this was our mapping study that was finished, and we enrolled 40 patients. I'm almost finished. Primary objective was mapping accuracy in the manual and our so-called automatic mode. Primary safety objective, no significant adverse events. Inclusion criteria were standard criteria for patients who would have ablation, except these patients consented to have the mapping procedure with our system first. And there were exclusion criteria of no ischemic VT or AF. And our preliminary results, which we presented at our various international symposia, were very good. I won't bore you with the fact, other than brag, that we had very good results, and no significant adverse events related to our system. So conclusions. Real-time electromagnetic control of the electrophysiology catheter is provided by this system. It's a true closed-loop system, as Josh was saying, fully integrated with a 3D mapping system that's commercially available. There are 2 of them out there, and we are likely to develop a 3rd of our own, but 2 of those, and we're going to be fully integrated with both. Currently, we're integrated with one of them. Servo control to keep the catheter tip at desired anatomic site and going back to that site and keeping it at that site, which is an incredible feature. Adequate tip force creates transmural lesions, as I showed you in animal studies, and no special shielding of EP lab, as Josh told you in great detail. Initial clinical results are very encouraging, and we're now undertaking ablation protocol. So with that, I don't know if it's OSHA approved, but this is the train where everyone is trying to jump aboard. But we think we're starting something exciting and new in the way we treat arrhythmias in clinical electrophysiology. So thank you very much. And